So this problem wants us to they give us two complex numbers and they want us to multiply them together and divide them. And we're like, we already know how to do that, right? If you wanted to do z1 times z2, you could just do z1, oopsie, I can write, z1 times z2, and you would just expand it, right? So you have root 2 minus I root 2 minus another I root 2, and then plus I squared root 2. And then you would recognize that I squared is -1, so you're really subtracting root 2. So root 2 minus root 2 would go away. And if you have minus I root 2 minus another I root 2, you have minus 2 I root 2's. And you're like, cool, I can already do that. Why is that in this chapter? Because for some reason they want it in polar form. So it's not going to save us any time here. This was pretty fast, but just to show that it works, we're going to do it in polar form. So this was our old method, just multiply them out. But our new method is to write them in polar form first and use our little rule about polar form. And this is going to save us time, not now, but later on when we have to do this to a bigger power. So, but right now we're just kind of checking that it makes sense. So first we have to convert these to polar form. We're going to go root 2 on the real and down root 2 on the imaginary. So root 2 on the real, down root 2 on the imaginary. We recognize this as a 45, 45, 90 triangle. So this would be just a 2 there, if you just multiply that by root 2. If you don't see it, you can do Pythagorean theorem. But we should recognize it as a 45, 45, 90 to be able to get that angle there. So our radius is 2, and our angle is 7 pi fourths, starting here, going there. So if we really wanted to, we could write z1 as 2 times the cosine of 7 pi fourths plus I times the sine of 7 pi fourths. All right. And we'll do the same thing with z2. So we have 1 on the real, -1 on the imaginary, so we're down there. So 1 on the real, -1 on the imaginary, so we have 1, 1, root 2. Again, they've picked nice 45, 45, 30, 60, 90s for us. And this angle is going, so our radius is root 2, and our angle is going to be 7 pi fourths again. And so if we really wanted to, we could write z2 as root 2 times cosine 7 pi fourths plus I sine 7 pi fourths. And so our rule is that if we're multiplying complex numbers together in this form, we can multiply their radii and add their angles. So if I wanted to do z1 times z2, I could multiply their radii, so 2 times root 2 is 2 times root 2, and add their angles. So 7 pi fourths plus 7 pi fourths is 14 pi fourths. And plus I sine of the same thing, 14 pi fourths. Now, just to clean it up a little bit, 14 pi fourths is the same as 7 pi halves. Just reducing that fraction, 7 pi halves, 7 pi halves. And then 7 pi halves is coterminal. Like 7 pi halves is bigger than 2 pi, right? 2 pi is 4 pi halves. And so if I went around, that'd be 4 pi halves, 5 pi halves, 6 pi halves, 7 pi halves puts me right down there. So 1, 2, 3, 4, 5, 6, 7 pi halves puts me down there. So that's coterminal with just a pi halves. So this would be the nicest polar form answer. 2 root 2 cosine pi halves plus I sine pi halves. And the question asks for polar form, so this is where we would leave it. Now if you're curious, if it matches the old way we did, all you have to do is convert it back to standard form by just figuring out what these are. The cosine of pi halves is 0, and the sine of pi halves is -1. So distributing this, we definitely get 0 plus or minus 2 root 2. root 2i. So this is indeed minus 2 root 2i, which totally matches the old method that we got before. Oh, amazing. So this was a lot more work though. Right now the polar form is a lot more work, but believe me, it has its uses later on. But right now, it's just kind of, hey, that works, okay. All right, I'll do the division in the next video.